So we have some graph problems that we're going to evaluate and map out using this equation. It's the displacement velocity and acceleration versus time graphs, which we're already familiar with, but so using this, we're going to map this out. So we'll just read this first. It says, based on the image above, right here, sketch a displacement versus time, velocity versus time, and acceleration versus time graphs for this process. A man walks from the tree to the house. He begins with an increasing velocity for the first 3 meters. He gets tired, therefore stands still a while. He starts walking again at a steady pace, then gets increasingly slower as he stops at the house. So first off, we can already rule out any negatives in displacement because we know it starts at 0, so he will only ever be going forward. And that's the only reason I made this line lower, is so we would have enough room. But so that will help us a lot when figuring out where our displacement graph is going to go. It will also help a lot to figure out the entire displacement graph first, then we move on to velocity and acceleration. So starting with displacement, it says a man walks from the tree to the house. That's where he's going, he's always going forward. He begins with an increasing velocity for the first 3 meters. We can just assume where 3 meters is, and a key point is always treating this line as your starting point. So in displacement, we know he's always getting farther and farther away from the starting point no matter where he is. So, or stays that far away. So he begins at an increasing velocity, meaning he's always speeding up. So our displacement line will be a curve because it's getting faster and faster and faster. So that's going to look something like this. It's not very clear, but a curved line because it's getting faster and faster. From there, it says he gets tired and therefore stands still. So standing still is going to show he's not moving, but he's still that far away. So we have to show that he's standing still, so the line will be just straight across because he's not moving, but he's still that far away. He's still however many, 3 meters away. So then from his standing still, he's regaining the energy and he starts to walk again at a steady pace. Steady meaning he's going the same velocity each step he takes. He's not increasing or decreasing speed. So that means our line will be a constant upward slope because he's steadily getting farther and farther away from your starting point, which we treat as this line. From there, he increasingly slows to a stop. So he's still getting farther and farther away from the tree, which we can act as this line. He's still getting farther and farther away, but he's slowing down as he goes. Therefore, if this curve is speeding up, we know that slowing down curve has to look something like this. So it's curved because he's going up and then he stops, making it a straight line. So curves up, 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 stops straight. You have the opposite curve because this is increasing, decreasing. Oops. Now an easy way to just figure everything out from displacement to velocity and then acceleration is to figure it out one step at a time. So what I like to do is just draw a dotted line so you figure out each one by itself. And that will help us with our graphs. So taking into consideration velocity. Velocity is the speed in which you're going a specific direction. So starting with green, because that's only what we're focusing on first with velocity, is the increasing speed for 3 meters. Because this is increasing, it's a curved displacement line, we know that velocity is going to be a straight increasing steady slope. Because displacement increasing at a steady speed, velocity, he's going faster and faster, therefore he's increasing at a steady rate. So that gives us our velocity. Next, we want to look at the time he stands still. So he's not moving at all. Therefore, there can be no velocity. Because he's no moving, there's no speed in which he can be moving. Therefore, we know that velocity is going to be at 0. Then, from there, we have our red line, which is the part where it states he starts walking again at a steady pace, getting farther and farther away from the tree. So because it's at a steady rate, it's a increasing slope for displacement, we can figure that it's going to be a horizontal straight slope at 3 meters, because he's still moving, but he's not increasing at a certain speed, he's staying at that one speed, therefore the line stays at this one speed. From there we have our orange, which represents how he slows to a stop. Therefore, we can figure that because this has to be horizontal this way, with this slope, we know that it decreasing through this type of slope will give us, he starts at this speed and he's increasingly getting slower and slower and slower. So his speed is increasing downwards because slower, right? And then from there, we can just connect the 2 zeros, and that gives us our velocity. So moving down to acceleration, mainly focus on the velocity graph. So we determine velocity from displacement, now we're going to determine acceleration from velocity. So the green, it's an increasing velocity, therefore it's this level of acceleration for the entire time. Next we have our purple column, and because velocity is 0, that means there's no velocity, so we can have no acceleration, because acceleration is the velocity, so there is no acceleration. Acceleration is the rate of increasing or decreasing velocity. Therefore, because there's no increasing velocity or decreasing, there can be no acceleration. There's no acceleration when there's no increasing or decreasing velocity. Therefore, the next orange statement shows us that it is decreasing, therefore there will be an acceleration. However, that acceleration is going to be negative because the speed is going down. That means that acceleration has to be in the negatives because it's going in the negative direction. So then when you match these two, that's what your acceleration graph is going to look like. So these are what your 3 graphs will look like after putting them all together sort of as one without the colors and without the dotted lines. So this should be how your graphs match up on an all around together scale.